Welcome friends. In last two lectures we discussed radiative heat transfer between black and grey surfaces. For a problem involving one or two surfaces, the solution method is relatively straightforward and one can solve analytically. But it is very difficult to keep track of the equations when the number of surfaces involved in radiative heat transfer are large. In this lecture, we will discuss a method based on electric networks to solve the radiative heat transfer problem in a grey enclosure, where the enclosure is divided into a number of surfaces. So, the discussion of this method starts from the same equations that we discussed in the previous lecture on grey surfaces. So, we write an energy balance on a surface. We have an enclosure and on surface element we can write the energy balance. The flux Qi is basically the difference between the radiosity, which includes the emission from emittance and reflection, minus total irradiation. Okay. So, this is the heat flux or energy balance on surface I. Qi is equal to Ji minus Hi. Now, for the grey diffuse surface we have to substitute for irradiation Hi. So, irradiation can be written as summation over radiosities from all the surfaces. So, summation j is equal to 1 to n Jj and the view factor between the two surfaces Fij. So, Fij and Jj, okay, minus H naught I, which is the radiation coming from outside. Okay. This is outside radiation which may be coming from some outside source. Okay. So, Qi is equal to Ji minus summation Jj Fij minus H naught I. Okay. We can also write this expression as Qi is equal to summation j is equal to 1 to n Ji Jj, reason being the summation rule, summation I j is equal to 1 to n Fij is equal to 1. So, using this summation rule and substituting it in this equation, we can write down Qi in terms of difference between the radiosities between two surfaces. So, Ji minus Jj is the difference in radiosities between the two surfaces and multiplied by the view factor between the two surfaces, we can write down the heat flux on surface I and definitely the outside irradiation H naught I. Now, what we do is the total energy transferred through radiation from surface I. Okay. So, from surface I, the total amount of energy transferred through radiation can be written as Qi times Ai. So, we multiply by the area Ai and we write it as capital Qi. So, Qi is equal to Ji Jj and we have taken the view factor in the denominator. We write this as 1 upon Ai Fij minus Ai H naught I. Okay. Or we can also write this as summation j is equal to 1 to n Qij. Now, this is the total energy transfer between two surfaces. So, Qij is the total energy transfer between the two surfaces I and j minus Ai H naught I. Now, there is a specific reason why we have written this equation in this particular form. Okay. So, it will be clear on the next slide. Okay. So, Q1 or so this is the heat transfer between two surfaces. Okay. So, definitely if one body is gaining energy, the other body may be losing the energy, and the direction of Q1 and Q2 are opposite to each other. If Q1 is losing energy, Q2 will be gaining energy. Okay. We have this factor 1 upon A1 F12 Okay. This factor is basically defined as radiative resistance between the two surfaces, okay, and J1 is radiosity and J2 is radiosity. We also define J1 minus J2 as potential, okay, or radiative potential. So, what we have basically done is we have used the concept of electric networks to define this problem, okay. So, we have radiosities of the two surfaces as potential. The difference between radiosities is the potential difference, and the view factor 1 upon A1 F12 as the radiative resistance, okay. If we know the radiosities, using the method of electrical analogy, we can calculate the current or heat transfer. Q1 is equal to minus Q2 is equal to J1 minus J2 upon this resistance 1 upon A1 F12, okay. So, this is the potential, we basically write in electrical analogy as delta V, and this is the resistance we write in electrical analogy. So, V is equal to IR. So, here also we have the potential difference J1 minus J2 divided by the radiative resistance 1 upon A1 F12, okay. Now, we have another equation that relates black body emissive power and radiosities Ji to the heat flux. So, Qi is equal to epsilon, where epsilon I is the emittance of the surface upon 1 minus epsilon I, and then the difference in radiative the emissive power of the body and radiosity of the body, okay. This particular equation can be simplified, okay, by writing the total energy transfer Qi, which is same as in the previous case, okay. The energy transferred is same. So, Qi is equal to Ebi minus Ji upon 1 minus epsilon I Ai epsilon I. This particular term in the denominator is called surface resistance, okay, and definitely this is going to be same as J1 minus J2 upon 1 upon A1 F12, okay. So, the current is going to be same, okay. So, we write this as in electrical analogy, electric network methodology, the 2 points are at potential EB1 and J1. EB1 is the black body emissive power, J1 is the radiosity. The resistance is 1 minus epsilon 1 A1 epsilon 1, this is called surface resistance, and Q1 is basically the current or the heat transfer, okay. We can combine these two resistances into a single network like this. So, we have EB1 followed by a resistance of 1 minus epsilon 1 upon A1 epsilon 1, this we have is J1, and then we have radiative resistance of 1 upon A1 F12, and we get to J2, and then again we may have EB2, again we have 1 upon epsilon 2 A1 epsilon 2, okay. And if there is no other surface, the current throughout is going to be the same, okay. If Q1 is current here, so this current will be uniform here, okay. So, it will be minus Q2, where Q2 has direction in this, in the reverse direction, okay. So, for the two surfaces, if there are only two surfaces, the current is going to be uniform because it represents the same network connection, okay. There is no parallel connection into this network. So, it is just a single serial connection. So, current is going to be the same, or radiative heat transfer is going to be the same. So, for infinite parallel plates, we can combine the resistances in series, okay. As I have drawn there this network, we have 3 resistances. The 2 resistances are surface resistance, one resistance is radiative resistance, as is also shown here, okay. So, 3 resistances can be added together. So, combined resistance R in series is R1 plus R2 plus R3 in series. So, we have added the 3 resistances, and then the total potential difference between the two ends is EB1 and EB2, and the current or radiative heat transfer Q1 at this end is simply the potential difference EB1 minus EB2 divided by the total resistance, or at the other end it will be the same because it is the same network, no parallel connection. So, we have Q1 is equal to minus Q2. Okay. So, this is how we can basically apply the method of electric network to solve simple problems. Okay. We can have multiple surfaces in an enclosure. We can represent the enclosure with a finite area surfaces. There may be n surfaces in all. So, for these n surfaces we can define junctions. Okay. So, we have in this particular network the current that is reaching at this node. We can write this current as the difference between the potential along this resistor, across this resistor. So, EBI minus JI is the potential difference, and then the surface resistance 1 minus epsilon I AI epsilon I. Now, this current or heat transfer between these junction has to satisfy the summation law of the current. That means, the radiative heat transfer at this point should be sum of the radiative heat transfer in all the networks. Okay. So, we write using the summation law, J is equal to 1 to n, the potential difference in each arm Ji minus Jj divided by the radiative resistance of each arm or each network. Okay. Now, the surface may be exposed to external irradiation from sun or some other source outside the enclosure, that will be added separately to the radiosity. Okay. So, we have added the component of the external irradiation separately at the radiosity of surface I. Okay. So, total heat transfer from surface I can be written as Qij, where Qij is the radiative heat transfer between surface I and j, all the surfaces we have taken into account, and then extra radiation from the outside source. So, so this is a very simple method that basically allows us to solve complicated problems having multiple surfaces, multiple gray surfaces, and we want to solve for heat flux or unknown black body emissive power of a particular surface. This method can be applied to find out potential, that is the temperature, or current, that is the heat flux in any arm or any surface. We can apply this method. So, we will apply this method to this problem. In this problem what we have is again a solar collector. The solar collector basically consists of a collector plate. Okay. The plate has a temperature of 77 degrees C. This is the collector plate. It has emittance, it is black, the emittance is 1. Now, as we have already discussed in previous lectures, we want solar collectors to absorb maximum radiation, but we also want that they should not emit significant amount of radiation. Okay. So, what we basically has been done in this case, the solar collector has been covered with a glass which is totally transparent to solar irradiation. Okay. So, we have this is the glass plate. Okay. The solar radiation is falling vertically with an intensity of 1000 watt per meter square. The atmospheric temperature is given at 70 degrees C. There are 2 side plates also. These are the 2 side plates on the collectors which are insulated and have an emittance value of 0.5. Okay. The reflectance of the glass plate is given as 0.9. The dimension of the collector is 1 meter by 1 meter, and 10 centimeter is the height of the side plates. In addition to radiative heat transfer, we have also convective heat transfer in this problem. Although this is a point of discussion of a different lecture where we will combine radiation with convection, but here we have a convection on the top surface. So, top surface has convection with a heat transfer coefficient of 5 watt per meter square Kelvin. Any effect of free convection inside the enclosure. So, free convection inside the enclosure is neglected. what we have to find out is total amount of energy collected by the collector with this glass cover and without glass cover. So, let us solve this problem using the electric analogy. So, first we will draw the network and then we will basically solve this problem. So, let us draw the network first. So, we have surface 1 which is at the bottom, and let us call this EB1. Okay. It is black, so there is no difference in radiosity and the emissive power. So, EB1 is equal to J1, that is they are equal because the surface is black. Okay. These are the side plates, we call it J2, okay, is equal to EB2. Here also we have J2 is equal to EB2. There is no potential difference. So, because the plates are insulated. So, for two cases we have EB1 is equal to J1 when the surfaces are black and when the surface is insulated. So, the surface 3 or side plate surface 2 is insulated, and that is why J2 is equal to EB2. There is no flux or current in this arm. This is J3 and this is connected by the radiative resistance A1 F13, okay, and then this is EB3, and this value is the surface resistance 1 minus epsilon 3 A3 epsilon 3. Okay. Now, for a radiative problem, this network is good enough. Okay. We have radiation from sun. So, for radiative heat transfer this problem is good enough, but we have convection also. So, we have to draw another network here. So, we will draw it here from the top surface, where EBA is the emissive power atmosphere, which is maintained at 17 degree C, okay, and this resistance is R3, let us say atmosphere. Okay. So, this is the network for the problem. Now, we will solve this problem for the heat flux Q1, because we are interested in how much energy is collected. So, Q1 can be written as the total amount of energy transfer from surface 1, that is the collector, is equal to sigma T1 power 4 minus TA power 4. So, we are basically dealing with this point and this point. Okay. This is the network, we can just draw it again, EB1, and then this is the combined resistance and EBA. Okay. This we can call as R. Okay. So, we are trying to simplify the above network with this simplified network, where we have multiple resistances in parallel and series. The end to end potential difference is EB1 minus EBA, that is sigma T1 power 4 minus TA power 4, that is end to end potential difference, and then R. Okay. This is the amount of flux, and then we have also the radiation from the sun. Okay. Outside irradiation we have taken it separately. Let me just show you this point once again. So, we are taking the external irradiation separately. Okay. That is what we have done here also. So, A1 is the area of the collector and QS is the Q solar is the solar irradiation, which is 1000 watt per meter square. Okay. Now, we first try to find out this value of R. Okay. So, let us see. So, first of all let us call this point 3, this is point 2. So, is the resistance, effective resistance between point 1 and 3. So, what we have is these two are in series and this is in parallel. Okay. So, R13 is equal to 1 upon A1 F13, okay, plus 1 upon A1 F12 plus 1 upon A3 F32. Okay. So, these are in the series. Okay. This is the resistance which is equal to 1 upon A1 F12 and this resistance is equal to 1 upon A3 F32. Okay. So, these two resistances are in series, that is why we have just added them and then taken inverse, and these two are combined with A1 F13 which is in parallel. So, this is the effective resistance and we can just simplify this as A1 F13 plus 1 by 2 A1 F12, where we have assumed or observed that F12 is equal to F32 because of the symmetry in nature. Okay. So, F12 is equal to F32. Okay. So, we have half F12 and this becomes equal to A1 F13 plus half F12. Okay. Now, we can find out the values again using the view factor tables. The value of F13 can be calculated and it comes out to be 0.827 and value of F12 is equal to 0.173. Okay. And with this the resistance R13 is equal to 1.095 1 upon meter square. So, note down the dimension of the view resistance, radiative resistance, it has units of 1 upon area. So, 1 upon meter square. So, value of R13 is 1.095 meter square. Okay. So, with this our network looks like this. This is 0.1, this is 0.3, this is R13. Okay. And then we have another resistance to EB3 and then another resistance to EBA. Now, this is a serial network. So, we will solve this. So, the resistance R3A is little complicated. So, first of all let us find out R3A. Now, this point we will understand in a different lecture. Basically, here we have combined radiative and convective heat transfer, and the resistance R3A includes the effect of radiation as well as convection. So, it is important that we write an energy balance and try to find out this resistance. So, the heat transfer through convection and radiation from the top surface is equal to sigma T3 power 4 minus Ta power 4. Okay. A3, this is due to radiation. So, we are writing the energy balance on the top surface, top plate, top surface that is exposed to the sky, okay, not the surface of the top plate which is exposed to the cavity. Okay. So, this is the top surface. So, this is the radiation part, the heat transferred from the top surface through radiation, and definitely we have to multiply by epsilon 3 the emittance plus the convection part which will be equal to H A3 T3 minus Ta. Okay. This is the convection part. Okay. So, we write this as in terms of radiative potential we have to write. So, we write it this as epsilon 3, so sigma T3 power 4 minus Ta power 4, okay, A3 epsilon 3 plus H T3 minus Ta upon sigma T3 power 4 minus Ta power 4. Okay. So, this is what we have basically defined. Okay. Now, we define the resistance A3 epsilon 3 plus H by sigma T3 minus Ta upon T3 by 4 minus Ta power 4. Okay. So, this is a complicated expression for the resistance, combined radiative and convective resistance at the top surface. Okay. Now, we have to simplify this expression. So, we write this as equal to A3 epsilon 3 H sigma. Now T3 by T3 minus Ta we take in the denominator, and this becomes equal to 1 upon T3 cube plus T3 square Ta, T3 Ta square plus Ta cube. Okay. So, this is the thing. Now, as compared to the other resistances like radiative resistance and surface resistance, which is a surface property or property of orientation of the two surfaces, this depends on temperature, okay, through the convective heat transfer coefficient. So, this resistance is a function of temperature. So, we have to kind of simplify this. So, how do we simplify this? So, we simplify here by assuming that the temperature difference between atmosphere and this glass plate is not going to be significant, and it is not going to affect the resistance R3A in a big way. So, we assume this value and we just approximate R3A as A3 epsilon 3 plus H sigma 4 Ta cube, okay, where atmospheric temperature is known. So, all the quantities now are known, okay. So, this is now known, okay. Otherwise, the problem cannot be solved by hand, you will have to incorporate computer to solve this problem, because the resistance will then become the function of temperature T3, which is not a known variable, okay. So, from this we can calculate 1 upon R3A as equal to, so this is actually I did a mistake here. So, this is 1 upon R3A. So, 1 upon R3A is equal to A3 epsilon 3 plus H upon sigma 4 Ta cube is equal to epsilon 3 value is given as 0.9, okay. The value of H is given as 5 watt per meter square Kelvin, and Ta is given as 17 degrees C. So, we substitute these values, okay, into this. A3 is given as 1 meter square. So, all these values we substitute and we get the value of 0.554 meter square. So, this is the resistance between the top surface combining radiation and convection, okay. Now, we have all the variables. So, we have all the variables, we have this resistance, we have this resistance, we have R13, okay. So, we can combine this into a single and calculate the value of heat flux using this expression. So, the value Q1, I will just solve it here. Q1 is equal to, from this expression, Q1 sigma T1 power 4 sigma T1 power 4 minus Ta power 4 upon the combined resistance R minus A1 Q solar minus A1 Q solar, okay. So, sigma T4 T1 power 4 T1 the temperature of the plate we know, okay, that is 77 degrees C. So, 273 plus 77 power 4 minus the 17 degree 273 plus 17 power 4, okay. Combined resistance, now they are in series, okay. So, we have to just add the 3 resistances R13 plus R this resistance 1 minus epsilon 3 upon A3 epsilon 3 and R3A A3, and when we have to multiply by A1 and Q solar, okay. Now, all these quantities we know. R13 we have already calculated, R13 value is 1.095 over meter square, R31 we have already calculated 0.554 1 upon 0.554, and epsilon 3 is also known 0.9. So, we have all the quantities. Q solar is 1000 watt per meter square, we substitute the values and we get Q1. So, this will be minus 744 watt, and the efficiency of the collector we can define eta as 744 by 1000, because the total amount of solar radiation coming is 1000. So, the efficiency is 74.4%, which is reasonably very good. Okay. Now, if you do not use this glass plate over the collector, how much energy will be basically absorbed. Okay. So, I will just do, so without glass plate, the energy balance Q1 will be equal to the radiation part A1 sigma T1 power 4 minus TA power 4. This is the radiative energy balance, and then the convection part H T1 minus TA. Now, the plate, collector plate will be directly exposed to the environment with the same heat transfer coefficient that we have assumed, minus Q solar. Okay. So, the area will be common. Okay. So, we substitute the values here and we get the value as minus 250 watt. So, the collector efficiency is simply equal to 250 by 1000, which is equal to 25%. Okay. So, compared to 75% with the glass plate, the efficiency has reduced significantly to 25%. Okay. So, that is why the glass the solar collectors are always constructed in such a way that they have two layers of materials, one which absorbs radiation and another surface which basically has little bit of transparency into it. So, thank you for your kind attention. I end this lecture on the network methods. In the next lecture, we will study some more methods, some more accurate methods to solve radiative heat transfer between black and grey surfaces.